Welcome back, everyone. I'm here on page 6 of the Chapter 4 lecture note outline, and we're here in part 2, where we're about to start talking about compounds, chemical formulas, and then start learning about how to name chemical compounds. So let's start here with the section about chemical formulas. So it turns out there are many ways that we use to depict chemical compounds. Some of these include the familiar formula that you're used to seeing with the symbols of the elements and the subscripts indicating how many of those elements there are. We also have a variety of two-dimensional and three-dimensional modeling techniques to help us depict and visualize what molecules look like. In this class, we'll focus on two of those methods. That is, chemical formulas and structural formulas. Chemical formulas are written symbolic representations for chemical compounds using element symbols, subscript numbers, and occasionally charge signs. Specifically, a chemical formula tells us what type and how many atoms of each element are present in a chemical species. Occasionally, it is also necessary to communicate some information about the charge present on the species, and in those cases, we indicate the charge. Finally, a chemical formula also might communicate information about the physical state of the species, meaning whether or not it is a solid, a liquid, or a gas. Here are some examples of chemical formula that demonstrate many of these features. First, we have carbon dioxide. We notice the elements carbon and oxygen, and then there's a subscript indicating how many of the oxygen atom are present in a formula unit of carbon dioxide. Another example is the hydronium ion, or H3O with a plus charge. This is an example of a similar situation, but here we have a charge being indicated because this is an ionized compound. Here's another example, calcium sulfate. Notice here that this formula has parentheses within it. You're going to see shortly why those parentheses are used and learn how to use them yourself when you write out chemical formulas. Let's go take a look in detail at these different features within chemical formulas and see how they work. First, let's talk about the meaning of the subscript that we see in chemical formulas. As an example, let's consider the formula N subscript 2, H subscript 4. The 2 and 4 are referred to as subscripts because they're written below the main line of the text. The meaning of these subscripts is quantitative. And by that, I mean they specify a quantity. The quantity that these numbers specify is the amount of a particular element within a formula unit of a chemical compound. So for example, if we had a single formula unit of this molecule, which is called hydrazine, it would have 2 atoms of nitrogen and 4 atoms of hydrogen in that single molecule. Now, we usually have much more than a single molecule or formula unit of a chemical compound, and these subscripts still work out on larger scales. They tell us the ratio of the different elements within that chemical species. So that's what the subscripts tell us. They tell us about the quantities of elements in a compound. Now, sometimes we also find superscripts or symbols in the superscript position on a chemical formula. This usually happens when we're dealing with something that's charged. So for example, we had hydronium earlier with the formula H3O with a plus charge in the superscript position. Because the plus charge is written above the line of the text, it's referred to as a superscript. And this is where we place charges. So for example, we might have a plus charge. Usually we just use a single plus symbol, and I tend to circle those so that they're emphasized. If we have multiple charges, say we had a -2 charge, we would write -2 or 2 negative up here as well. So if we need to indicate a charge on a species, we'll indicate the type of charge, meaning positive or negative, and the magnitude of that positive or negative charge with a numerical value indicating such. So if you're the inquisitive type, you'll probably have a lot of questions at this point, like what does this exactly mean if you have sulfur and 4 oxygen atoms and a 2 negative? What does that even look like? And those are all really good questions, and we're going to have to answer them kind of over the course of the entire semester. So just be patient with yourself. Also be patient with the course. We're going to get there. It's just going to take a little bit of time as we move forward. So for now, let's go on to the next page, and we're going to continue learning a few more parts of chemical formulas. And as we start to build on these concepts, I think some of those questions will be answered in due time. Now, as you saw earlier, some chemical formulas also have parentheses within them. What do these parentheses mean, and how do we use them correctly? Let me show you. As an example, let's consider the formula for the chemical compound known as magnesium hydroxide. Magnesium hydroxide has a chemical formula with magnesium as the first element written. Then we have parentheses, and inside of those parentheses, we have something that's called hydroxide. This hydroxide has the formula O with an H next to it. And then outside of this closing parenthesis, we have a subscript 2. Let me explain what some of this means. The first thing that I want to explain is the meaning behind these parentheses. These parentheses you can think of as being a container for the elements that are within them. So it contains elements. Now here's the thing about parentheses. We only want to use one of these containers when we have more than one element to place inside of them. And when I say more than one element, what I mean is more than one type of element. So notice here we have two types of elements, O and H, and I'm containing those elements within the parentheses. So that's one of the first things to note. We only use parentheses when we want to contain more than one type of element, like hydroxide here. Let's refer to the stuff here within the parentheses, the thing that the parentheses are containing, as a group of atoms. What's required to have a group of atoms? Well, you need to have more than one type of atom. So let's write this down first. Parentheses are used to contain a group of atoms. But that's not the only requirement we have in order to use parentheses. There's a second requirement. This second requirement is that you need to have more than one occurrence of that group in order to use the parentheses. So here we have two occurrences of this hydroxide group. So we use parentheses with a subscript 2 outside of them. There's another substance called sodium hydroxide that only has one occurrence of the hydroxide group. And notice here we don't use parentheses. That's because we only have one of these groups, and there's no need for it. So we can summarize all of this in a few words. Parentheses are used to contain a group of atoms. Specifically, we use them when there's more than one occurrence of that group. So for example, we have here a group of atoms. What makes it a group? There's more than one type of element. We have an oxygen and a hydrogen. That's a group of atoms. And there's more than one of those groups. We have two here. If we had only one of those groups, we wouldn't use parentheses. Now we're going to have a lot more practice with parentheses and interpreting what they mean on chemical formulas a little bit later on in this lesson and in the subsequent lessons. Let's do one example before we move on. Here's a formula for a compound known as iron 3 sulfate. Soon you'll be learning how to determine the name for a variety of chemical compounds like iron 3 sulfate. But for now, let's just see if we can interpret what this formula means. When I look at this formula, my mind automatically divides it up into the different components that are within the chemical formula. For example, seeing the number 2 next to the symbol for iron tells me there are 2 iron atoms. I also see we have parentheses grouping up sulfur and oxygen atoms in a particular ratio that I happen to know is called a sulfate. And because of the subscript 3, that tells me I should have 3 sulfate groups. Altogether, my mind visualizes this in a number of different ways, one of which looks something like this. I visualize 2 iron atoms and 3 sulfate groups. Notice there I said sulfate groups. I didn't say 3 sulfur atoms or 12 oxygen atoms, because that would be thinking about the sulfate group as individual sulfur and individual oxygen atoms, when that's not the case. Notice here that we're using parentheses, and the parentheses tells us the stuff inside of the parentheses is a group of atoms that's stuck together. We just have multiple occurrences of those, and in this case we have 3 occurrences of the sulfate group. So right now, this is the stage I would like you to be at. I'd like you to be able to look at a formula and be able to identify things outside and inside parentheses, and maybe put together a little visual picture like the one I've done here. Now, what I'm about to show you is a little bit beyond what you currently know, but you'll be learning it soon enough. Specifically, it has to do with the charges on the iron and the sulfate group. Now, it turns out that the reason why iron 3 sulfate has this particular formula with 2 iron atoms and 3 sulfate groups has everything to do with the charges on the iron atoms and the sulfate groups. So as you'll be learning, the sulfate groups actually have a 2 negative charge for each one. So if you have a 2 negative here, a 2 negative here, and a 2 negative here, that's a total of 3 times 2 negative, which is a total of 6 negative charges from sulfate. Now here on the iron side, we have to balance out that negative charge with a positive one. How do I know that? Well, that's because I know that iron 3 sulfate is completely neutral overall. It doesn't have any excess charge. So if we have 6 negative charges, that means we also have to have 6 positive charges. And how do we get 6 positive charges? Well, we have 2 iron atoms to do that. So if each one contributes a 3 positive charge, we would balance out the 6 negative charge with 6 positive charges. And this is why iron 3 sulfate is called iron 3 sulfate, because each iron has a 3 positive charge. So now that we've gone into some detail on chemical formulas, which are the main formulas that we're going to be using in this class, I also want to just give you a quick glimpse into one other way that we use to describe chemical compounds, and that is the structural formula. In Unit 3, you will learn the fundamentals of drawing structural formulas from regular text chemical formulas. The structural formula tells us the same information as a regular chemical formula, but adds some additional information. For example, structural formulas also indicate how and where atoms are connected on a given species. From this information about how and where atoms are connected on a molecule, we can interpret this and derive other important properties about a molecule, such as its shape or its reactivity. To show you what I mean, I'm going to show you an example of a chemical formula, which is 3 carbons, 8 hydrogens, and 1 oxygen. So we get C3, H8, and O. Now, if you continue on in chemistry, you'll learn the way in which these atoms can bond together in a field known as organic chemistry. And when we bond these atoms in the correct way, we can derive 2 different chemical compounds with the same chemical formula. They're different in the way the atoms are connected. So for example, in this first drawing, we have the oxygen atom connected at the first of the 3 carbon atoms. This is referred to as 1-propanol, and it's a gas at room temperature. Now, another version of this chemical formula is where the oxygen is connected at the second carbon atom. And this is not called 1-propanol, it's called 2-propanol, because that oxygen is connected to the second carbon atom. Another more common name for this molecule is isopropanol, and you can buy this at the grocery store as a liquid. Turns out that if you get more into the study of what these structures mean, you can actually interpret them to know ahead of time that the one on the left is more likely a gas and the one on the right is more likely a liquid. So as I mentioned earlier, you'll get some skills on how to draw and interpret structural formulas a little later in the course, but for now we need to go back to learn some other fundamental information. And that brings me to section 3, which is the section on nomenclature, or how we name chemical compounds. Because we'll be looking at several different types of chemical compounds, we will necessarily learn several different naming systems. So let's go ahead and get started and learn how we name chemical compounds. First, the way we name chemical compounds is based entirely on the type of substance that we are naming. We will be dealing with 2 types of chemical compounds that we have to name. One class of chemical compounds that we'll be naming are referred to as molecular compounds, and the other category are referred to as ionic compounds, or salts. So we have molecular compounds and we have ionic compounds. We apply a different system of naming to each of these categories. So the first step for you is learning how to differentiate between molecular compounds and ionic compounds. So let me show you how we do that. And I'm going to start by just drawing some formula examples for each of these categories, And then we're going to look at those and see how we differentiate them. So up here, I'm writing down some formulas for molecular compounds like carbon dioxide, nitrogen dioxide, glucose, and sulfur trioxide. Now let's take a look at some formulas for ionic compounds, otherwise known as salts. Here I have the formulas for sodium chloride, silver oxide, iron 3 oxide, magnesium carbonate, and sodium sulfate. Now, before we even talk about how to identify the molecular versus ionic formulas when you're looking at them, the first thing that I want you to notice is the subtle difference in the way I name some of these compounds. So for example, this formula here, which is nitrogen with 2 oxygen atoms, is called nitrogen dioxide. This is called sulfur trioxide. Now I'm going to go down here to some other formulas and I want you to compare the difference to what I say. This is called silver oxide. This is called iron oxide. Specifically, it's actually called iron 3 oxide. This is called magnesium carbonate. This is called sodium sulfate. Now, do you notice the subtle difference in which I named these differently? If you notice that sometimes I said things like di and tri up here on the molecular compounds, you're actually getting a head start on how we name things differently in chemistry. I used things like di and tri up here, like carbon dioxide, nitrogen dioxide, sulfur trioxide, but I didn't say that down here. I just said silver oxide, iron oxide, sodium sulfate. So that's one important distinction that you will be learning about. Now let's go into the details of how we actually differentiate between molecular versus ionic compounds. And what I want you to do is pause the video, look at these, and also look at your periodic table and see if you notice the big difference between these two types of compounds. And when you unpause the video, we'll discuss. So what do you think? Can you distinguish between molecular and ionic compounds by looking at their formula? Yes. And how do we do that? Well, notice the different types of elements that we have in molecular compounds. In molecular compounds, notice that we have all non-metals in the formula. Carbon is a nonmetal, oxygen is a nonmetal. Nitrogen and oxygen are also both nonmetals. In glucose, we have a bunch of nonmetals. We've got carbon, hydrogen, and oxygen. Sulfur trioxide, that's also a formula that has all nonmetals, sulfur and oxygen. What about ionic compounds? Do those have nonmetals only? No. Notice in ionic compounds, we have both metals and nonmetals. We have one type of metal, and we have sometimes one type of nonmetal, other times there's more than one type of nonmetal. But altogether, it's a metal with some type of nonmetal. So we have molecular compounds, which are all nonmetals, and then ionic compounds are a mixture of metals and nonmetals. So that's the first step in learning how to name compounds is look at the formula and try to determine if you're looking at a molecular compound or an ionic compound. Once you know that, you'll know which rule set to apply in naming it. Now what we're going to do is go on to the next page and learn how to name one category of compounds. That is, we'll learn how to name molecular compounds. In the next lesson, I'll teach you how to name ionic compounds. One of the unique things about naming molecular compounds is that we specify in the name the actual quantity of the types of elements present. You might have noticed me doing this when I named some of the molecular compounds on the previous page. For example, I said carbon dioxide, sulfur trioxide, etc. When I did that, I was specifying the numbers 2 and the numbers 3 by using something called a Latin prefix. We use these Latin prefixes when we name molecular compounds. Let's review the Latin prefixes for the numbers 1 through 10. For each value, 1 through 10, we have a special Latin prefix that we use to describe that number. For example, for the number 1, we use the Latin prefix mono. For number 2, we use di. For number 3, we use tri. For the number 4, we use the word tetra. For the number 5, we use the word penta. For number 6, we say hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. We use these Latin prefixes in a variety of contexts throughout language. So for example, we'll put them in front of a word to specify a number, such as the sides in a polygon. For example, we'll say a polygon, or a hexagon, or a heptagon, or an octagon, etc. We use them in chemistry to specify the number of a particular element. So for example, if I say dioxide, that means I'm talking about 2 oxygen atoms. If I say tetrasulfide, that means I'm talking about 4 sulfur atoms, etc. Now what I want to do is show you how to put together the name for a molecular compound using these Latin prefixes. I think the easiest way to learn this is actually to look at a number of examples and then discuss each one. We're going to start here with this first example, which is a molecule we all know, it's CO2, and that is called, of course, carbon dioxide. First, we write the name of the first element, and then we write the name of the second element, and we modify these two parts of the name with various things. So for example, in this case, we have 2 oxygen atoms, so we modify oxygen to have a di in front of it. But we also modify that second element in a particular way. Notice here I've changed the name of the element from oxygen to oxide. That's because it's the second element in the name. And this is what we do with molecular compounds. We write the first element unmodified and then the second element as an IDE ending. In addition to modifying the end of the element name with this IDE suffix, we also have to put in the Latin prefix before the element explaining how many of those atoms there are. So for example, with carbon dioxide, because we have 2 oxygen atoms, we put the Latin prefix for 2 in front of that name. So it's dioxide. Let's take a look at another example. Here I have a single carbon atom and a single oxygen atom. So how do we apply this rule in this case? Well, first let's write down the name of the first element, carbon. The name of the second element is oxygen, but remember, let's modify that from oxygen to oxide. So here I have carbon oxide, but I need to put in the Latin prefix explaining how many of the oxygen atoms I have. How many do I have? That's right, just 1. What's the Latin prefix for a single element? That's correct, it's mono. So this would be called carbon monoxide. Let's take a look at this next example. Here we have nitrogen, and there are 2 atoms of nitrogen, with oxygen, and there are 5 atoms of oxygen. Go ahead and pause the video and take a moment, see if you can write down the name for this molecule. And when you unpause the video, we'll discuss. So the first thing we're going to do is write down the name of each of the elements in the molecule's formula, which is nitrogen and oxygen, but we're going to modify the second element, oxygen, to have that IDE ending. So far I have nitrogen and oxide written down. What else do I need to do to complete the name? Well, that's correct. I need to put in the Latin prefixes. So what Latin prefix should we use before nitrogen? That's correct. Because there are 2 nitrogen atoms, we should have the Latin prefix di. What about the prefix for oxygen? There are 5 oxygen atoms, so we should use the prefix pent. So when all is said and done, we get the name dinitrogen pentoxide. So if you got that one right, great job. Let's try the next example. Here we have a single iodine atom and 3 bromine atoms. Go ahead and pause the video and see if you can write down the name for this molecule. Okay, so where do we start with this? First, we have to write down the name of the first element, that's iodine, and then we need to write down the name of the second element, but with an IDE ending. How do we transform bromine to have an IDE suffix? That's right, we go from bromine to bromide. So we should have the name iodine and bromide, but let's not forget to put the Latin prefixes in. What prefix should we have in front of the bromide? Since there are 3 bromine atoms, we would say tribromide. Now what about iodine? There's only 1 iodine. Should we say mono or should we not? Well, that's an interesting part of the rules. Notice here on carbon dioxide and carbon monoxide, I didn't say monocarbon dioxide or monocarbon monoxide. It turns out on the first element, if there's only one of those elements, we don't use the mono prefix in that case. So should I use the mono prefix here for iodine? No, I just say iodine and then tribromide. That's the correct name. So if you got that one right, great job. How about one more example? Let's try this one with 3 sulfur atoms and 2 phosphorus atoms. Go ahead, pause the video and see if you can write down the name. Okay, so let's follow our same format as before. We have first element followed by second element IDE ending. First element here is sulfur, and there are 3 of them, so we can say trisulfur. And then we have 2 phosphorus atoms. Now, what do we do to the phosphorus to give it an IDE ending? Turns out we say phosphide. So we have trisulfur diphosphide. Before we wrap up, let's just write down a few of the most common of the nonmetals that we see as a second element, and then I want to show you how their name is transformed from the regular element name like oxygen into the IDE suffix version of the name. So far we've already seen oxygen, which is transformed into oxide. We've also seen bromine, which transforms into a bromide, and we've seen phosphorus, which transforms into phosphide. What about nitrogen? Nitrogen transforms from nitrogen into nitride. Iodine transforms from iodine into iodide. For fluorine, we get fluoride. For chlorine, we get chloride. And for selenium, we get selenide. So now we've learned how to identify and name molecular compounds. Molecular compounds have all nonmetals, and we name them by writing down the name of the first element, followed by the name of the second element with an IDE suffix, and of course we use Latin prefixes to indicate, in each case, how many atoms there are. In the next lesson, we're going to learn about how to name ionic compounds. For now, I hope you're doing well. Please let me know if you have any questions, and I will see you in the next video.